Hi everyone, in last part we solved to check for the primeness of a given number using 5 methods, and in this video we are going to see for the primeness of a range of a given numbers. So if you have not watched the last part, I would suggest that you go and watch the part 1 in which I have explained 5 methods to check for a primeness of a given number. So before proceeding to the methods to check the primeness in a given range of numbers, let me first recap what we did in the last part. So in last part we checked for the primeness of a given number using 5 methods, and the first method was to check from 1 to n. Second method to check from 2 to n minus 1. In third method from 2 to n by 2, and in fourth method it was 2 to root of n. And in fifth method, that is the optimization or the fourth method, and that optimization is 6k plus minus 1. Okay, so this is the optimized version to check for the primeness of a given number. Now problem 1. Let's say you have been given random numbers and you are asked to check for the primeness of a given numbers, these numbers, right? So let's say this is n1, this is n2, this is n3, this is n4, this is n5, and now you have to check whether the numbers are prime number or not. So what you will do, you will apply method 5 on each number and you will check whether that number is a prime number or not, right? So the time complexity of this approach will be square root of n1 plus square root of n2 plus square root of n3 plus square root of n4 and so on. Now we will find the upper bound, right? So let's say these are m numbers. So for m numbers, and let's say there is an n which is greater than or equal to n1 or n2 or n3 or n4, then the time complexity will be square root of n, right? So this will be the time complexity of this, and the space complexity is big O of 1 because we never used any space for any numbers. So that's why the time complexity is big O of 1. Now let's see second problem. Let's say you've been asked to find the prime numbers in a given range. So let's say 1 to 130. Okay, so you have to find the prime numbers in the range from 1 to 130. So the first method that you might try is apply the fifth method for each number. So the time complexity will be root of 1, root of 2, root of 3 and so on, root of 130, right? So this is the method that you would apply to each number, and by doing this you will be able to find which numbers are the prime numbers. So this will be the time complexity, because time complexity using the method 5 is square root of n. Okay, so for this it will be root of 1, for 2 it will be root of 2, for 3 it will be root of 3 and so on. So the time complexity will be m square root of n. So m is the number of queries, that is 1 to 130, and let's say there is an n that is greater than equal to 1, 2, 3 and so on. So we are finding just the upper bound. So let's say this is n1, this is n2. Okay, so let's say there is an n that is greater than all of this. So we can say that these are m numbers, and all m numbers has this complexity of square root of n. So time complexity is square root of n. Now the space complexity. So the space complexity will be big O of n, because for this method we have to store the numbers 1 to 130 in an array, right? And for each these numbers we'll have to apply the method 5. But if you have to just print whether the number from 1 to 130 are prime or not, then the time complexity will be big O of 1, because in that case you will run a for loop from 1 to 130, and for each number you will apply the method 5, and in that case you don't have to store 130 numbers in an array, right? Now let's see the better approach to solve this problem. Okay, so by applying method 5 on each number is not an optimized version. So the optimized version is using the algorithm Sieve. So we'll apply the Sieve algorithm on this. So let's say first we'll calculate for 1 to 30. So for that the numbers are, okay, so for Sieve method the 1 is marked as false, it is not a prime number, and this array of 1 to 30 all the numbers has been initialized as true. By true means all the numbers are prime number. 1 is marked as not a prime number, false. So we'll start with 2. So 2 is a prime number, but all of its multiples are not prime numbers. So we'll keep 2, but all of its multiples will be marked as false. So 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, then 28 and 30, right? Now we move to the next number 3. 3 has not been crossed out. What does this mean? This means that there was not a number before 3 that could cross out 3. This means 3 is a prime number. So we'll keep 3, but we'll cross out all the multiples of 3. That is 6, 9, 12, 15, 18, 21, 24, 27 and 30. Now we come to the 4. 4 is already crossed out, so we'll move forward. 5. 5 is again a prime number, right? So we'll keep 5, but we'll cross out all the multiples of 5. So first it will be 10, then 15, then 20, then 25 and then 30. Now we go to 6. 6 is crossed out. We move forward. We go to 7. So for 7 we'll cross out 14, 21, 28 and then out of the range. Okay, so we'll not check for the rest of the number, that is 11, 13, 17, and I will let you know why. Okay, so now if you see in this array, the numbers which are not crossed are the prime numbers: 2, 3, 5, 7, 11, 13, 17, 19, 23 and 29. These are the prime numbers. Now we don't have to check for numbers like 7, 11 and 13 because they will never cross out any number. Now let me show you why. Okay, so let's say for 2 you will first cross out 4, then 6, then 8, then 10 and 12 and so on, right? Now let's see 5. Okay, for 5 which one number will you cross out first? So you will cross out 10, 15, 20, 25, then 30. But now if you see these numbers, what is 10? 10 is 2 multiply 5, 15 is 3 multiply 5, 20 is 4 multiply by 5 and 25 is 5 multiply by 5. This is 5 multiply by 6. Now if you see for 2 what we did, keep the 2 but cross out all its multiple. So 2 prime number has crossed out its multiple. So 10 has been already visited by prime number 2. So 5 don't have to visit again, right? Then prime number 3 has already visited 15. So prime number 5 don't have to visit this number, right? Then for 20, this is 2 multiply 2 multiply 5. Prime number 2 has already visited 20. Why would 5 again visit it, right? Now this is 5 multiply by 5. This is the first number that 5 has to cross out. And then further 30, then 35, then 40 and so on. Right? Now let's see for 7. For 7, which one will we cross out? That is 28, 35 and 42, right? So what are these? This is 2 multiply 7, this is 3 multiply 7, this is 4 multiply 7, this is 5 multiply by 7, this is 6 multiply by 7, and then further 49, that is 7 multiply by 7 and so on. Now if you see this, 14 has already been visited by prime number 2's. Okay, this has already been visited by prime number 3. This has already been visited by prime number 2 multiply 2 multiply 7, prime number 2. This has already been visited by prime number 5. This has already been visited by prime number 2 and prime number 3. But this is the first number that 7 has to cross out first. But unfortunately this number is out of range. Got it? So that's why I told you that we don't have to check for numbers like 7 and numbers after it. So the last number that can cross out some numbers in the array is 5. How come 5? Because if you see for 2 we start with 2 multiply 2. So the 4 is the first number that 2 will cross out. For 3 it will be 3 multiply 3. For 5 it will be 5 cross 5. For 7 it will be 7 cross 7. Now if you see 5 multiply 5, that is 25, that is still less than 30, which means 20 will be crossed out by 5 only. But for 7 it is 7 multiply 7, that is 49. This is out of range. So 7 would never cross any number, right? So we don't have to check for that number. And if you also see that the square root of 30, okay, see this way. So for 7 it will be 7 multiply 7, that is 49, right? So what is this? This is a prime number p and this is p multiply p. So p multiply by p has to be less than or equal to what? Let's say this is right. So has to be less than equal to right. So what is p? P is less than equal to root of r, right? In our case it is 30. So 30 root of r is less than p. So it will be less than equal to what is square root of 30? It is something like 5 point something, right? So p has to be less than or equal to 5. What is p? P is a prime number. So p has to be less than equal to 30. So here p is 5. So these are the only prime numbers that would cross out something in this array. So now let's implement this algorithm and then we will see the time complexity and space complexity of this. So first we'll create a vector of bool to store whether this number is prime or not. So n plus 1 numbers all marked as true, right? Then 0 is not a prime number, 1 is not a prime number, so we'll mark them as false. These are not a prime number. Now we'll start with prime number 2 and we'll check until p cross p is less than or equal to n and then p plus plus. Now if this number is not a prime number, the number is already crossed out, okay, then we will continue to next number. Else starting from p multiply p, okay, prime multiply prime, for example 7, it will be 7 multiply 7, for 5 it will be 5 multiply 5, okay. So we'll do this j is less than equal to n and j plus equal to p. So first it will be 7 multiply 7, that is 49, then the next number will be 56, for example 5, it will be 25 first, then 30, then 35 and then 40 and so on. Then we mark is prime of this number as false. Finally we'll create a vector of int to store these primes. Then for I is 2, I is less than equal to n, I plus plus. Now we check if this is prime number, then we push this number into primes array, okay, and finally we'll return primes. So let's see what we did. So first we created a Boolean vector of is prime of n plus 1 length, all marked as true, which means all the number are prime number. Then we set 0 and 1 as not a prime number. Then we start with the 2 and p cross p is less than equal to n p plus plus. I'll let you know why we did this, okay. So if the current number on which we are is not a prime number, then move to the next number. Now at line number 11 we are on a number that is a prime number, right? And for that prime number we have to cross out all the multiples of that prime number, and the first number that will start is p multiply p and it has to be less than equal to n, and we will keep on incrementing that number with p. So for example for 5 we will start with 25, then we will increment by p, that is 5, that is then 25, then 30, 35, 40, 45 and so on, and we will make those multiples as false. Now this condition p cross p has to be less than equal to n. Now let's say for 1 to 30 you pick the 5, p is 5 here, then we come at 6, but 6 is crossed out by 2, so 2 or 3, okay. So then we continue to next number, then the next number is 7, so 7 multiplies 7 is not less than or equal to n. So we will not check for 7, right, we check until 5. So that's why we added the condition that p cross p is less than equal to n. Now let's check if this works or not. So our base case has been passed and now we will submit to check whether all the test cases are being passed or not. Okay, so all of the test case has been passed and now let's see the time complexity and space complexity of this algorithm. So let's take an example of 1 to 30 again, okay. So for the first prime number, this is a prime number p, then we have 3 as a prime number, then we have 5 as a prime number and so on, right? So for prime number 2, how many numbers will we cross out approximately? So it will be 30 by 2 numbers we will cross out approximately. For 3 we will cross out these numbers. For 5 it will be these numbers and so on. Now let me tell you one more thing. When I told you that for example 5, we have to start crossing the numbers from 5 multiply 5. For 7, we have to start crossing the numbers from 7 multiply 7 and not from like 7 multiply 6, 7 multiply 5. So this is just the optimization, right? So if you are at 5, you could start crossing from 10, then 15, then 20, then 25. But you have to start from 5 multiply 5 is just the optimization, because these numbers has already been crossed out by the prime number that is less than 5, right? Now let's see here. So here in the time complexity, when it is a prime number 2, we will approximately cross out 30 by 2 numbers. For 3, it will be approximately 30 by 3. 5, it will be approximately 30 by 5, and so on. Now if you notice, this is 30, 1 by 2, then 1 by 3, then 1 by 5, and so on. Now this is the sum of reciprocals of prime numbers. So these are the prime numbers, these, and these. So this is sum of reciprocals of prime number, and their sum is nothing but log of n, right? So the time complexity is, this 30 is nothing but n. Okay, so the time complexity is n multiply log of n, and this log of n is from this. So the sum of reciprocals of prime numbers is log of n. So the total time complexity will be n log of n. So now let's see next problem. So the next problem is segmented sieve. So let's say you have been asked to find the prime numbers in this range 1 billion to 1 billion and 1000. The first method obviously will be to apply the sieve method, and in the worst case you might want to apply method 5 of checking a prime number on all the numbers from 1b to 1 billion and 1000, right? That would be one of the approach, applying method 5. So that will give the time complexity of square root of n for a given number. Okay, so for each number you have to add up that time complexity. So this is one of the answer to this question. Now the next method that you may want to apply is sieve method. You might think that, okay, we have to find the prime numbers from 1 billion to 1 billion and 1000. So you might want to store all the number from 1 to 1 billion and 1000. But just because you want to find out the prime numbers from 1 billion to 1 billion 1000, you would store all the number from 1 to 1 billion and 1000. You are wasting a lot of the memory, because the total number from 1 billion to 1 billion 1000 is 1001. You have to find for only these numbers how many numbers are prime in this range, but you are storing all the number from 1 to 1 billion 1000 just to apply the sieve method. That would take too much time and too much space. Okay, so to solve this better, we will use the segmented sieve method, and to solve using segmented sieve, we have to revisit the sieve method. So let's see what we did in the sieve method. Okay, so let's take an example of 1 to 30. So what we did in this method, we first take a prime number, and then for that prime number we cancel out all the multiples of that prime number. Okay, we cross out all the multiples of that prime number. Then we find the next prime number, that is 3. Then we cross out all the multiples of that. Okay, then we find next prime number, and then we cross out all the multiples of that. So the process is have a prime number, then cross out its multiples. This was the method. So we have to follow this process until the square root of r. So for the range of 1 to 30, it will be until 5. So prime numbers until 5, that is 2, then 3, then 5. So for 2 it will be the multiples of 2, then for 3 it will be multiples of 3 cross out, and then for 5 it will be multiples of 5 that we have to cross out. So the process was that take a prime number and then cross out its multiple. Now in the segmented sieve, since we cannot apply the sieve method to store all the number from 1 to 1 billion and 1000, just to apply the sieve method, what we will do is we can first find the prime numbers and then cross out its multiple. Okay, so sieve method is different. In sieve method, we found a prime number, we cancel out the multiples, but in segmented sieve we first find the prime numbers. So to find the prime numbers in the sieve method, we have to find the prime numbers until square root of r. In this method, assume this as a virtual array. Okay, so we have to first find the prime numbers, right? We have to find until r, and r is 1 billion and 1000. So we'll create an array of primes that has all prime numbers in the range of 1 to square root of 1 billion and 1000. So this is one of the array. Now this problem is a sieve problem. Okay, so we'll find out all the primes in this range 1 to 1 billion and 1000 using the sieve method. Now we have prime numbers. Now the problem will be like, this is a virtual array. Okay, so 1 to square root of 1b and 1000, then all the way to right, that is 1 billion to 1 billion and 1000. This is our, so this is our array. Okay, so this is a dead zone. We don't want any operation in this zone, but this is a, let's say, safe zone. this is the zone in which we have to find out the prime numbers. We have these prime numbers already calculated in this array. Okay, so this is, let's say, P1, this is P2, this is P3, and this is P4, and so on. Now we have to just cross out the numbers in this safe zone. We don't want to apply any operation because we don't want to waste time, right? Because this portion is not required. We have to find only the prime numbers in the range of 1 billion to 1 billion and 1000. So for these prime numbers, we have to cancel out the multiples in this safe zone. Now if you remember sieve method, in sieve method we have a prime number and we will cancel out a number that is multiple of it, right? So we'll start with P2 cross P2. Now there are certain cases. What if this P cross P lies in this range? Okay, so the first case is if the P cross P lies in the dead zone, then we will find the first multiple in this range and start crossing from that value. Okay, so in this case we will find the first multiple in this range. Now the case 2. In case 2, what if P cross P lies here and the first multiple lies here? Which one should we pick? The first multiple or this P cross P? We will pick this. Why? So in the sieve method we already checked. For example, for 5, okay, we could have start from 10, then 15, then 20, then 25. Okay, but we picked 25 and not 20, 15 and 10 because they have been already crossed about the lesser prime number than that P. So for given prime number P, we have to pick this one, and this first multiple would have already been crossed out by a prime number that is less than P. Okay, so we will pick this P, this position we'll have to pick. Now let's see third case. In third case, in this range from L to R, the prime that is P cross P could lie here. In that case, the first multiple will also be the same as P cross P. In any case, it will not happen that first multiple is here and P cross P is here in L to R. Okay, in a given range L to R, it will never happen that first multiple will be here and then P cross P will be here. It will never happen because first multiple is by name, you can see first multiple. So P cross P itself will be first multiple in that case, right? So they can overlap, but the case could happen like first multiple here, then P cross P here. This could happen. So in that case, we have to pick this. Now in all the three cases, we have to pick the largest. And now let's see why. When P cross P is in dead zone, we will pick the first multiple. Again, the largest of these two numbers is this one. Then in second case, where P cross P is larger than first multiple, in this case, we will pick P cross P. Again, larger one. In third case, P cross P and FM are same. In that case also, we pick the larger one. So both are same. We can pick any one. Now let's see all the three cases using an example. So let's see for an example of, let's say we have to find all the prime numbers in the range of 100 to 130. Okay, so for segmented sieve, we first have to find the primes array. Okay, so for 130, the square root will be 11 point something. Okay, so the prime numbers from 1 to 11 will be 2, 3, 5, 7, 11. Now using these prime numbers, we have to cancel out numbers in this range. This is a dead range, right? So for 2, we have to start with 2 multiply 2, that is P multiply P. But this 2 multiply 2, that is 4, lies in the dead range. So we have to start with the first multiple in a given range of L to R. And the first multiple of 2 will be 100. So for 2, we'll start crossing from 100, then 102, then 104, right? And so on until 130. Now 3. For 3, the first multiple, that is P cross P, will be 3 multiply 3. But it lies in the dead zone. So we'll have to find the first multiple in the range of L to R. And what will it be? And that will be 102. So the first multiple is 102, that is divisible by, that is 3, right? And so on. Now let's see next one. So for 5, the first multiple will be 5 cross 5, but this lies in a dead zone. So we'll have to pick the first multiple in the range of L to R, and that is 100, and so on. Now let's see next prime number, that is 7. Similar process, 7 multiplies 7 lies in dead zone. So we'll pick the first multiple in L to R. Then comes 11. For 11, the first multiple will be P cross P, and that lies in the L to R. Okay, so in L to R, this is your 121, and what is first multiple of 11 in this range? That is, I think, yes, 110. So this is 110 and this is 121. So which one should you pick? P cross P you should pick, because what is 110? 110 is 11 multiplied 10. That is nothing but 2 multiply 5. So prime number 2 has already visited 110. Also prime number 5 has also visited 110. So why should 11 visit again and again? So the first number that 11 would cross out is 11 into 11. So this is the number that we will pick. Now let's see next example. So let's say we have to find all the prime numbers from 25 to 30. Okay. So the square root of 30 will be approximate, that is 5. So we have to find all the prime numbers until 1 to 5, that is 2, 3 and 5. Okay, so this is our range 1 to 25 and 30. This is dead range and this is the required range. So for 2, it will be 2 multiplied 2, but 4 lies in the dead zone. So we'll start with first multiple starting from 25. So what will be the first multiple? That will be 26. So starting from 26, we'll cross out all until 30. Now for 3, it will be 3 multiplied 3, 9. It still lies in the dead zone. You'll have to pick the first multiple in range from L to R. Now for 5, it is 25. That is P cross P. So the first multiple is also 25 and P cross P is also 25. So we'll pick the 25 and start crossing from 25 until 30. So this is it. Now first we will solve a problem based on the primes in this range, and then we'll see the time complexity and the space complexity of this algorithm. Now before proceeding to the primes in a range, let's see one caveat, okay, that we will have to solve. For example, there is a function that is primes in range that asks you to find the prime numbers in this range. For example, 25 to 30, or let's say 100 to 130, let's say 0 to 30, let's say 1 to 30. So this is solved by segmented sieve. This is solved by segmented sieve. But what about these? So these two problems will also be solved by segmented sieve. If so, while solving, you will see that we will create is prime array. Okay, so if the range start with 0, then the first element, okay, will be false. It will not be a prime number. And if the right, so this is right, if right is greater than or equal to 1, then the first element cannot be prime, because 0 and 1 are not prime. Okay, and if the range start with 1, then also is prime of 0th element is false, because 0 is not a prime number. So this is how this algorithm handles the ranges like 0 to 30, 1 to 30. Okay, so for example 0 to n or something. So both cases has been handled by this algorithm. So first we'll see the solution of this algorithm, and then we'll see the time complexity and the space complexity of this algorithm. So first we'll create a private method to return the prime numbers until a given limit. So vector of int will return primes until given limit. So we'll create a vector of bool to store the is primes. So this is the sieve method I am writing. So it will store numbers until limit plus 1. All are prime numbers initially, but 0 and 1 are not prime number. So we'll mark them as false. And then from 2, prime number 2 to p multiply p less than equal to limit and p plus plus. If this p is not prime number, then we'll continue to next number. Else if it is prime, we will cross out all the multiples. So we'll start with p cross p, and j is less than equal to limit, and then j plus equal to p, and is prime will be marked for this j as false. And finally we'll collect all these primes in a vector of int stu I is less than equal to limit I plus plus. Okay, and if it is prime, then we will store this in primes dot push back this I, and finally we'll return primes. So this is the sieve method that will return the prime numbers until a given limit. Now we have to write the code for segmented sieve. So for segmented sieve, as I told you, we'll create two arrays. One of the array will store all the prime numbers, and the other array will store only the range that we want to find out the prime numbers in. So for example, you remember that we take the example of 1 billion to 1 billion and 1000. So we have to store only those numbers, those 1001 numbers, that is 1 billion to 1 billion and 1000. So we will create two arrays. One of the arrays primes that we can find out using primes until a limit, that is square root of r, right? So we find out all the prime numbers, and now we will store the primes, okay, primes of actual range. So the total range will be r minus l plus 1, all are prime numbers initially. So the range L to R may be, for example, like from 10 to 30, right? But we will store these numbers in index 0 index based, right? So that's why we stored R minus L plus 1 numbers, that is 0 based index. Now for each prime number, for each prime in primes, we will find the start. So what will be the start? So first let's see, we haven't seen how to calculate the start of a number. So let's take an example of finding the prime numbers in the range of 1 to, that is 100 to 130. So for 130, the prime number was 11, right? So 11. So we'll calculate the primes, that is 2, 3, 5, 7, 11. Now for these prime numbers, we have to cancel out the multiples in this required range, right? Now let's say 5. So for 5 we have to start with p cross p, that is 25, but 25 lies in the dead range, right? So we have to find the first multiple. So its first multiple of 5 will be 100 in the range of L to R, where L is 100 and R is 130. So 100 is first multiple, but how come we find out 100 as the first multiple? So it can be found out by like this: 100 by 5, that is 20. So 20 multiplied by prime number, that is 5, will give us 100. So that's how we find out the first multiple. Now let's see for 3. Okay, how do you find out the first multiple for 3? Because for 3 also, p cross p, that is 9, lies in the dead zone. So the first multiple will be 100 by 3, that is 33 point something, right? We take the ceiling of this number, and that will be 34. Now 34 will multiplied by the prime number, that is 3 again. It will give us 102. So this is the first multiple in the range of L to R. So that's how we find the first multiple. And the short formula for that is, you can apply this formula also, but you can apply for like L plus P minus 1 divide by P and then multiply by P. So for example, for 3, it will be L will be 100, prime will be 3 minus 1 by P, okay, then multiply by P. So this is the integer division. Okay, you have to do integer division first. So that is 103 minus 1, that is 102, and prime number will be 3. So 102 divided by 3 is 34, and then multiply by 3 is 102. Okay, so we got the first multiple in the range of L to R. So now let's see for 5. That will be 100 plus 5 minus 1 by P, right? That P is by 5. So that will be 104 by 5. So this is an integer division. This will be 20.8. So this is 20.8, and since it is an integer division, it will be 20, right? Then we multiply this by p, that is 5, that is 100. So 100 is the first multiple. So we'll use this in the primes in range. So for a given prime number, what will be the first number from which we have to start crossing out? That will be maximum of either it will be p cross p, or it will be L plus p minus 1 divide by p, that is integer division, then multiply by p again. So this is the start. Now for this start, we have to start crossing out all the multiples of it. So for int I is equal to start, I is less than equal to r, and I plus equal to p, and we mark is prime for this as false. Now the range can be anything, for example 100 to 130, but we stored all the elements, that is 100 to 130, as a zero based index, right? So the start will be here. What will be the start? It will be 100 or more than 100 in case of 100 and 130 range. So I will be that, but we have to subtract L so that it will be zero based index now. Okay, so we mark these elements as false, they are not prime number. Now the additional edge cases. What if L is equal to 0? Range start with 0. In that case, is prime for 0 is false. And if the right is greater than equal to 1, which means the range also contain 1 as a number, in that case is prime for 1 is also false. But what if L is equal to 1? In that case is prime of 0 is false. Now finally we'll create a vector of int to collect all the primes, that is final primes. Okay, so for starting from int I is L, I is less than equal to R, I plus plus. So if this is prime, so if I minus L is prime for zero based index, we subtracted L from I. Now if it is prime, then we have to push this inside final primes dot push back the I, and finally we'll return final primes. And now let's see if this works or not. So it says is prime 0 and 1 is false. This is wrong. So for is prime 0. So it will be is prime and not is primes. And then primes until, so it will be vector of int of primes, primes until, and it gives us the segmentation fault. So in the sieve method, it will be is prime of limit plus 1, all are true, 0 and 1 will be false. Then from p is 2 to p cross p less than equal to limit p plus plus, and if it is not prime number, then we'll continue. But if it is a prime number, then we'll start with the multiples of that prime number until j is less than equal to limit and j plus equal to p. Is prime of j will be false. Finally we create a primes array, and then from 2 to less than equal to limit I plus plus, we'll check if it is a prime number, then we'll push it inside the primes. So our sieve method is correct. Now let's see for segmented sieve. For segmented sieve, we first find out the primes until the square root of r. Then we'll create a boolean of the actual range is prime. For r minus L plus 1, all are true by default. Okay. Now we'll start with prime in primes. So for each prime number, we'll first find out the initial start value. That is either it will be p cross p, or it will be L plus p minus 1 divide by p and multiply by p. So for I is equals to start, I is less than equal to r, I plus equal to p, is prime of I minus L is false. That's correct. Now if L is 0, is prime of 0 is false. If r is greater than equal to 1, is prime of 1 is false. If left is equal to 1, is prime of 0 is false. Now we'll create a vector of int of final primes and from I is equal to L, I is less than equal to R, I plus plus is prime of I minus L. If it is a prime, then we'll push it inside final primes dot push back I, and finally we'll return the final primes. So this seems correct. Let me just refresh this and submit the solution again. So for L is 1 to 10, our solution returned to 3, 4, 5, 6 and 8, 9, 10, which is wrong. Okay, so we did mistake inside sieve method. We returned inside the for loop. Okay, so that's our mistake. So we'll have to take out outside of these loops. Okay, so now we'll check, and our base case has been passed, and now we will submit. And all of the test case has been passed, and now we will discuss the time complexity and space complexity of this algorithm. So for segmented sieve, there are two phases. Phase 1. So phase 1 was to find out the prime numbers until 1 to square root of r. So to find the square root of 1 to n, what was the time complexity using sieve method? It was n log of n, right? Now to find the prime numbers in the range of 1 to root r, it will be root r log of root r, right? So this is the time complexity of phase 1. Now phase 2. Let's see here. So in phase 2, what we'll do is, so let's take an example of that 1 billion number. So 1 to square root of r, then left and then right. So the left was 1 billion and this was 1 billion and 1000, and this was square root of 1 billion and 1000, right? So we find out the prime numbers in this range, right? So these are the prime numbers. For these prime numbers, we have to cancel out the elements or the multiples of these prime numbers in a given range of L to R. So for given prime number, we have to cancel out the multiples in this range of L to R. So similar to sieve method, we have prime numbers and we have to cross out not the whole numbers but only limited numbers. So in the sieve method, the time complexity was n log of n. Here it will be r minus L plus 1 multiplied by log of square root of r. Okay, so for phase 2, the time complexity will be this. Why? N is the number of elements that we have to cross out. So it will be r minus L plus 1. Okay, and the time complexity, this time complexity is the sum of the reciprocals of those prime numbers, right? So in this case, we have to find the prime numbers until this range only. So sum of reciprocals of these prime numbers would be log of square root of r, right? So the total time complexity will be, for phase 1 plus phase 2, it will be root r log of root r plus r minus L plus 1 log of root of r. Now let's see space complexity. So for space complexity, we created two arrays. One is primes array and the one is an array that contains all the elements from left to right. Okay, so the time complexity of this one, storing the primes from 1 to root of r. So the space taken will be root of r plus the space taken here will be r minus L plus 1. So this will be the total space complexity for this algorithm. Just to recap, in the segmented sieve, we first find the prime numbers and then we cancel out the multiples of those prime numbers in a given range of L to R. In a sieve method, we find a prime number, we cancel its multiple. We find a prime number, we cancel its multiple. But in sieve, since we cannot store all the values from 1 to R, because it will require a lot of memory. For example, 1 billion to 1 billion and 1000, we cannot store 1 to 1 billion and 1000. Just to find out the prime numbers in the range of 1 billion to 1 billion and 1000. Okay, so for that, we create two arrays. First, we find the prime numbers. So for a given range, the virtual array 1 to 1 billion and 1000, if we assume this is our array, to solve this using the sieve method, we first have to find the prime numbers, right? So first prime number, then cross. In segmented sieve, we first find out the prime numbers until 1 billion thousand. So these are the prime numbers which we first find out. So this will be our first array, and then 1 billion to 1 billion thousand, then this will be our second array. We will not store these numbers anywhere because that's the dead zone. Okay, so using these prime numbers, we cross out numbers in this range, and that's how we will be able to find out the prime numbers in this range. So again, let's see the code. So in this, what we did is, we first find out the prime numbers until square root of r, right? So we have the first array. Then the second array is the numbers itself in that range. Now using the prime numbers in that primes, we cancel out all the multiples in the range of L to R. After doing that, we collect all the prime numbers in final prime and we return the primes. So for range of L to R, we have to find the prime numbers from 1 to square root of R, right? So until square root of R, we find out the prime numbers using sieve method, simple sieve method. And that's how we solve for the segmented range.